promised, this talk is completely independent from the previous talk and independent from the talk tomorrow. So even if you haven't been here yesterday, you're good to go. So I'm going to talk about a sequence of works with these great people. So this is Mitali, Nikhil, Noam, and Zhiwei. And it's again about PCP and something. And in this case, the something is going to be high-dimensional expanders and routing protocols. So before I talk about anything like that, let me remind you what PCP is. So we kind of explained what it is yesterday, but I'm going to show it again in a different way. So what is 3SAT? So I give you a 3CNF formula, just like on a board. The question is phi satisfiable? Is there an assignment to the variables of Boolean values that satisfies all of the clauses? So we know the famous Cook-Levin theorem that says that 3SAT is NP-hard, namely it captures the essence of the entire class NP. And for now, we're going to think of the problem of verifying whether a given 3CNF formula is satisfiable or not. So we're going to think about it as a problem where you're given a formula, you're given some witness, and you're going to use that witness to check whether the formula is satisfiable or not. So the most trivial verifier you can think of is the witness is just the assignment, and the verifier just goes over the clauses one by one. It reads the first clause, x1, x2, x3, reads the three variables from the witness, checks if it's satisfied. Next clause. So that's the most trivial verifier you can think about. So let's talk about this trivial verifier again, but with a slight twist. Let's now think about it as a randomized verifier. So now the verifier is going to sample one of the clauses randomly, read the three variables in it, and based on it, decide to accept or reject. If that clause is satisfied, he accepts. Otherwise, the verifier rejects. So what's the performance of this? Well, one thing which is nice is that the verifier only makes three queries to the witness. It only reads three variables, which is good. This is something that we want. This is the locality that one often talks about. So now, what are the other two properties? Well, there is the completeness, which is what is the probability that the verifier accepts the formula in case it is satisfiable? Here it's just going to be 1. And there is the soundness. Suppose the formula is not satisfiable. What is the probability the verifier accepts in that case? Well, this verifier is a little bit too naive. It has very good completeness, but the soundness is not great. So if phi is not satisfiable, then whatever assignment you give me, at least one of the M clauses is not satisfied. And in the case that I chose that specific one, M is the number of clauses. Yeah, so maybe there is only one clause that is not satisfied. So the best I can say is that the verifier accepts with probability at most 1 minus 1 over M. So this is a soundness which is very weak, and oftentimes we want to amplify it. We want to get better soundness. So how do we improve that? Well, now enters the PCP theorem, so I'm not going to tell you exactly how to do that. I'm going to tell you that it is doable. So here is the PCP theorem. It tells you that there exists some other verifier, some strange verifier, and that verifier gets the formula phi and a witness W. Another witness is going to be from, the alphabet is going to be from some symbols set sigma, which is not 0, 1. It could be 0, 1, 2 if you want, but it's a minor point. And the length of the witness is going to be polynomial in the previous witness. Let's say n to the 10. So this new verifier gets the formula and the witness. And now what the verifier is going to do is going to make two queries to the witness. And based on the two symbols that it reads, decide to accept or reject. And the promise that we have about this verifier is this following. If phi is satisfiable, then there exists indeed some witness that makes the verifier accept with probability 1. And if phi is not satisfiable, then no matter what witness you give me, the verifier is going to accept with probability bounded away from 1. Let's say at most 0.99. Okay, so this is a really, really important result. This is called the PCP theorem.
Sorry,
N is the number of variables, or you can think about it also as the length of the witness, the original witness. Yeah. Yeah, so this is a great theorem. So some comments that I should make. So as I said, for technical reasons, the alphabet size cannot be 2, but it's still constant, like 3 would do. And the length of W is polynomial, which usually we think of as good. The completeness is great, soundness is multiple away from 1. It satisfies everything that we ever hope for. But you know, in life, whenever you get something, you say, oh, can I do any better? So let's see. Let's fine tune the details. Let's see what better we can hope for. And I could give several lectures about how you can try to improve this. But today and tomorrow, I'm going to focus on only 2 aspects. So what would be a better PCP theorem? First of all, we can hope for a better soundness. So 0.99 is great when you start off with 1 minus 1 over m. But you're not going to bet your life on 1% advantage. You'd want soundness which is much smaller. And also, if you look at applications, for example, in hardness of approximation, this is crucial. You want soundness to go down to 0. So that's one. Secondly, well, the length of the witness, it's polynomial, which is good, but polynomial is sometimes too large. So if you remember the independence, it's completely different, but the independence for Michael's talk, he was stressing a lot that the length of the witness or the questions is not depending on this and that. So it's out of the same spirit. You don't want the witness to blow up too much. You want to keep it as compact as possible. So in fact, these are the 2 questions that we are going to address today and tomorrow in my talks. And I'm not going to give you any examples of where, or I will give some examples of where these things come in, but these 2 considerations come in different areas in TCS, and beyond that, for very different reasons, and yeah.
Like you're insisting on 2 queries, right? Like that's the outcome.
Yeah, I'm insisting on 2 queries. Yeah. So at least from the place that I come from, which is hardness of approximation, 2 queries give you a lot of power, 3 queries give you almost nothing. Yeah, like if you want hardness results for stuff like vertex cover, set cover, you need 2 queries. Yeah. Yeah, but you're right that once you have more than 2 queries, things become easier.
The alphabet is large.
Sorry?
The alphabet is large.
In what context?
With 2 queries. What's the set of them?
In this theorem?
Yeah.
Constant. Yeah. Okay. So let's look at these 2 questions, and let me tell you some background on what is known. So the first thing, which I mentioned yesterday, and I'm going to mention again today, is the operation called parallel repetition, which is a very natural operation when you have some decent soundness, but you want to improve it. So if you apply this result, you can indeed improve this 0.99 soundness to any small constant that you wish, but as we'll see, it has some costs. If you want to go, below constant soundness, you can actually do that. It gets hairy, and these works do that. But these works get more than 2 queries. So if you want to get sub-constant soundness and 2 queries, you have to work even harder. And this was done first by Moshkovitz and Raz, and then by Dinur and Harsha. They got some variant of the classical composition technique. I'm not going to say anything about that, which is query efficient, and that buys you sub-constant soundness and 2 queries. Cool. So now what about the length? Well, as I said, the original proof of the PCP theorem gave some polynomial bound. Probably not too bad, but nobody computed the constants, as far as I know. And the first people that care about the size were Polisuk and Spielman, that almost entirely solved the problem, or seemingly. They got near linear size with soundness which is close to 1. So they got a little bit more than n, and to the 1 plus epsilon with soundness 1 minus epsilon. And not completely comparable result, Benson and Dan got even closer to linear. They got something that I'll call quasi-linear, which means just n times polylog n. But the soundness wasn't quite bounded away from 1, and at the same time it was better than this 1 minus 1 over m. So they got some nice soundness and quasi-linear size. And finally, Irit in 2007 gave a proper quasi-linear size PCP with soundness 0.99. So this improves this Benson-Sudan result. And for that, Irit came up with a completely different way to prove the PCP theorem, which is combinatorial, uses stuff which kind of develops into high-dimensional expanders as, I mean, we'll not see it, but it's in the background. And yeah, so that's what is known about these two problems. Any questions? Okay. Okay, so let me elaborate a little bit on parallel repetition, and we'll see what it gets, what it doesn't get, and this will also motivate for us some interesting questions. Okay, so here is the problem. I have this magical verifier, VPCP, that the people from the 90s constructed for me. It makes two queries, and it has soundness 0.99. And now I want to use it in a black box way to construct a new verifier that has smaller soundness. So what should I do? Well, just run it k times, right? Run it once, check if it accepts or reject. Run it again and again and again and again. So that works.
But that suddenly needs to be only 2 queries, right?
Yeah, but the way I described it, it does 2 times k queries, where k is the number of repetitions. And as I said, we want to keep the number of queries to be 2. So we want to implement this idea, but in somewhat hackish way, so that this will count as 2 queries. So I already said that. So what is parallel repetition? So parallel repetition amounts to saying, we'll do this thing, we'll attempt to run VPCP k times, but we'll sort of do it in parallel. So what do you mean by that? Well, originally, VPCP has this witness W, which contains a bunch of locations. Now, the new verifier, which I'm going to denote by VPCP tensor k, is going to have a lengthier witness. Each index in the new witness corresponds to a selection of k places in the original witness. So that's the idea of parallel repetition. That's what you hope to do. To completely discard the verifier now, what I'm going to do is I'm going to run VPCP k times. It's going to generate for me 2 k tuples. I'm going to look at my new witness, check these 2 k tuples, and then check. Okay? That's the new PCP. So the completeness is easy. If I had originally a witness which VPCP accepts with probability 1, as Michael said, I can tensorize it k times, I win. Now the soundness, this is the hard part, and this is what is called the parallel repetition theorem. It says that if the original VPCP accepts with probability at most 0.99, then no matter what you give me as this new witness, the acceptance probability is going to be decaying exponentially in k. And what is the exponential decay is even that is a difficult and fascinating question, which people spent a lot of time studying. But this is what is called parallel repetition. So you see that indeed if I take k to be large enough, I can drive the soundness down to be any small constant that I wish. But it has 2 issues. So if my original witness was of length m, then the new witness is going to have number of locations, which is roughly m choose k. So let's call it m to the k. So the witness length grows polynomially in k, or in the size of the previous witness. So that's one issue. In particular, I can never use this thing to get near linear, quasi-linear, anything. Like I do k equals 2, done. The second issue, which we'll stress about tomorrow, is that if you care about what is the trade-off between the alphabet size that you get and the soundness that you get, it turns out that you cannot get the optimal things using parallel repetition. So while parallel repetition is very, very powerful and very useful, it does have disadvantages. Okay. So here are the two questions that we're going to deal with. So today we're going to try to deal with the problem of how to amplify with less blow-up in the size. Ideally, we would like the blow-up to be only linear, like I managed to amplify and only multiply the length of the witness by 10. That would be ideal. We're not going to achieve it, but that would be kind of the holy grail. And secondly, what we're going to discuss tomorrow is if I fix the alphabet size to be Q, what is the best soundness you can get? And here the best you can hope for is 1 over Q, and the question is, can you get that or anything close to that?
So the linear blow-up is not automatically a linear PCP, right? Like you want to start with a PCP and make it better. How should I think of, or is it like a linear PCP?
So if you go to the word linear, then it's a bit of a loaded word because even how you represent the graph starts being a question because that's like a factor of log n. If you ignore all of these representation issues, then yeah, kind of. But again, it's a bit of a loaded question. So, yeah. Okay, so are the two questions clear? Okay, the first question, and I can tell you the main result for the talk today. So the main result, this is from a paper by Bafna, Nikhil, Vyas, and myself, and it's based on a bunch of works that I'm going to mention later, is that there indeed exists a PCP of quasi-linear size, namely n times polylog n, which has soundness epsilon, which is a small constant, as small as you wish. Okay, and the proof relies on a bunch of stuff. Some of them I know, some of them I don't know, have any idea about. So it uses high-dimensional expanders. I know a little bit about that, and we're going to see that. But it uses a bunch of other stuff, like periodic numbers, which like you can ask Alice about. And yeah, so it does use a lot of stuff. And I'm going to try to give you some intuition about some of it. And I'll try to highlight what I think is, at least for me, the most surprising aspect of this, which is the connection to distributed computing. But before that, let me tell you some applications of this result, just that you see what the size of a PCP has influence on. So here is one sample application. You can write a bunch of other applications like that, but one is enough. So it says the following. Assume the exponential time hypothesis, which is kind of well-believed hypothesis, I think, in TCS, saying that 3SAT has no sub-exponential time algorithm. So we assume that there is no sub-exponential time algorithm to decide whether a given formula is satisfiable or not. The conclusion of the theorem is that if you give me slightly less than sub-exponential time, 2 to the n over some polylog, then not only can I not distinguish between satisfiable and unsatisfiable, I cannot even distinguish between satisfiable and at most 7 over 8 plus a little bit satisfiable. Okay. I mean, this is like a direct corollary of PCP, like there is nothing fancy going on here. Another application, which is not application, yeah?
The polylog n depends on epsilon. How should I think of it?
Yeah, it depends on epsilon and quite badly. Yeah. In fact, I couldn't even tell you how it depends on it.
You couldn't?
Yeah, I couldn't. Yeah.
Instead, if we have a PCP of polynomial size, what will we get for the hardness result?
Sorry, say again?
If we only have PCP with polynomial size, what will instead?
So if let's say the size of the PCB was n to the 10, then instead of this 2 to the n over polylog, it would be 2 to the n to the 1 over 10. Cool. So another application, which is not an application of the theorem, but rather of the technique, is something called fault-tolerant distributed networks. So I'm going to explain what it is, but I'm just going to sort of say in buzzwords. So we show how to construct graphs that have small degrees, but at the same time they're well connected enough that you can distribute the messages over them in a way which is fault-tolerant. Like even if you corrupt a little bit of the graph, things are still going to go well. We'll define this thing very explicitly. But, yeah. So now let me tell you some really concrete stuff and tell you some ideas in the proof. And I'm going to focus on two components. The first component is direct product testing. And again, this is a very interesting question which deserves a lecture by its own, but I'm going to only discuss it kind of briefly. So what is direct product testing? Well, direct product testing is a problem introduced about 25 years ago by Goldberg and Safra, and their motivation was, we have the PCP theorem, the proof is quite complicated. Let's try to break it into parts and simplify some of them to make it more accessible. And they identified this component, which is called direct product testing, and then studied it by itself. And this is the following problem. Suppose I have some function f, which maps the numbers 1 to n to sigma. And at the back of your mind, you should think of this function f as an assignment to a formula. Like this range 1 to n represents the variables, and sigma represents the values that the variables may get. So I have some function, think of it as an assignment, and I want to encode it using the direct product encoding. So what is the direct product encoding? Direct product encoding is another function, which I'm going to denote by capital F, which takes k-tuples of previous variables and assigns them k-symbols in the following way. So it assigns the variables a1 to ak, what little f assigned to a1 to ak. Simple as that. If you recall what we did in parallel repetition, this is exactly how you tensorize the honest witness.
No, this is set to set because the A's appear as a set and the F's appears as a tuple.
Yeah, so that's a good question. So imagine that there is some canonical ordering on 1 to n so that whatever I wrote here makes sense. Like A1 to AK are ordered according to the canonical order. Cool. So this is the direct product encoding of the function little f. And just like in parallel repetition, when somebody gives me the witness to the tensor PCP, there is no promise that this is going to look like this. The same here. Nobody is promising me that capital F is going to look like that. So I should come up with some way to verify that a given function is indeed of this form. And this is exactly the direct product testing problem. I give you an assignment that assigns to subsets of size k to each one of them k symbols. I want to test locally whether it is a direct product of some little f as above. Okay. So I should explain this word locally here. By locally, I mean, I'm not allowing you to read all of capital G and take your time with that. I allow you to read capital G at 2 locations. That's it. Okay. So, yeah, so this is a really nice question, and there's been much research about it, so this is a very partial order of papers about it, and there have been many applications to it. And once I tell you that you can do 2 queries, your hands are tied behind the back, like what can you even do? So if you think about it for a little bit, the following natural test makes sense. So sample 2 sets, A and A prime, of size k. Okay, I should look at G at 2 places. Let's pick 2 places. Now, if you think about it, if A and A prime do not have any intersection, GA and GA prime are completely independent, like there is nothing to test. So we're going to take A and A prime that can set at size k, a square root of k.
Can you give a heuristic by square root? Like what is the...
anything not too close to k or not too close to 1. Yeah. So once I take this a and a prime, I observe that if capital G is indeed a valid direct product encoding, then whatever is in the intersection should have the same value in the coordinates. So this is indeed what I check. I check that GA and GA prime assign the same values to A intersection A prime. And this is the reason that I wrote it as a vector, just that it makes sense. Like nothing is going on too deep here. So now after this slide, we know what is the direct product encoding of a function, and we know what is the natural direct product test. Okay. So it's very easy to see that if capital G is a valid direct product function, test accept with probability 1. The harder and more interesting case is what happens if it's not the case. What if G is far from direct product functions? So we're going to state it in the other way around. So suppose that I have some G that passes the test with non-negligible probability delta. Can you say that it has anything to do with some direct product function? Well, the answer is yes. So here is an example result by Dinur and Golderberg. So they proved that in that case, there exists now a function little f defined over the base set, where capital G and little f agree on at least polydelta fraction of the sets A1 to AK. To the experts here, I'm slightly lying, but no worries, it's fine. But this is a really nice result. It tells you that even if you have a little bit of acceptance in the test, it still means that globally you should look a little bit like some proper direct product function. And as I said, this is a really nice result. And in fact, you can use this result, this combinatorial result alone, to get some amplification procedures for PCPs, which are kind of like parallel repetition, but are easier to prove. But of course, the major downside of this is that the blow-up in this procedure is just like in parallel repetition. If I ask you what is the size of the encoding of capital F compared to little f, it goes to the power k. So therefore, I'm not going to be able to use something like that to amplify myself without a blow-up in the encoding size. So we should do something different. Okay. So this is the classical direct product testing problem. So now we get to the question of, is there a sparse version of this business? Is there a sparse direct product encoding and sparse direct product test that still makes sense? Cool. Okay. So now we come to this very nice paper of Dinur and Kaufman, who are both here. And they suggested that high-dimensional expanders should be a way to approach these sparse objects. Namely, they proved that if you take any old spectral expander, then it's going to be a good direct product tester in the case the delta is close to 1. So namely, if you care about the case where the test passes with probability almost 1, then any spectral expander does it.
In what sense high-dimensional expander is spectral or co-boundary expander?
Spectral. Spectral. So that's a theorem. And they conjectured in the same paper that there should be some high-dimensional expanders that provide for you a sparse direct product encoding and testers, even in the case that the soundness delta is close to 0. But yeah.
What do you mean by sparse? Like, what is sparse there?
So that's the next click. That's the next click. So there is this joke of what is a good question, great question. So that's the next click. Yeah, so what is sparse? So I'm going to say what HDX is in a moment, but really what a sparse direct product test really amounts to is choosing a subset of the K-sets, which is sparse, which is only of size O of n.
set is S.
Yeah, so the S would correspond to the subsets that I want to keep, and I don't want to keep too many of these subsets.
The set is going to be the set of simplices in the scatter?
Yeah, so the set S is going to be the top faces in some, or maybe not top faces, but the faces in some simplification topics. Cool. So I want to highlight one thing about the quantifiers. So the first theorem here says that any spectral expander does a trick for delta close to 1, but the conjecture says that there exists some HDX. And you can ask whether any HDX does it. So that turns to be not the case. So there's something going on here. Okay.
What do you mean by OK? Means n times 2 to the k.
OK just means C sub k times n, where C sub k is some function of k. It's not too terrible of a function. It's like 2 to the k squared, or something like that. Okay. So just to explain, once you choose the set calligraphic S, and the choice here is clever, like it's not something that you're going to write on the board and be done with it. But once you make that choice, everything is forced. The encoding is forced, and the test is forced. There is no more freedom. The encoding is the same, and the test is the same. So it's really all about the choice of S. And this conjecture turns out to be true. And this was proved together with Bafna and Lifshitz and independently by Yotam Dickstein, Irit, who is here, and Alex Lubotsky. And these two, and again, it relies on many other works by many great people. And together this says that indeed for any delta greater than 0, there exists some sparse direct product tester where the soundness of the test is delta. I'm suppressing many details here, but that's good enough for now. Okay. So that finishes the discussion about direct product testing and sparse direct product testing. We're going to return to it maybe later. Maybe I'll say a few words about it. But we require this component in our construction of PCPs. This is going to be the way that we are going to amplify soundness from 0.99 to something close to 0. So now let me discuss the second component, which is distributed computing. Now this is going to look completely different, and towards the end of the talk, I'm going to tie them up together. So here is a completely different problem from a completely different talk. I give you a graph G. It has vertices V, it has edges E. Now I give you pairs of vertices, S1T1 up to SMTM. Think of M as linear in the number of vertices. Now the setting here is that each one of the SIs has a message, MI, that he wishes to deliver to TI. But the graph is not to your liking, and there is no edge between SI to TI. So to pass on that message, SI should start sending it to its neighbors, and then they send it to somebody else, and so on and so forth, until it gets to TI. So this is what is called routing. You want to route messages in a graph. Now, what do we care about? Well, one thing that we care about is the number of rounds in a protocol. So in each round, as we said, the vertex is allowed to send a message to its neighbors. So we want to be able to, for the SIs to deliver the message to all of the TIs in small number of rounds. So our goal is to design a graph G, which is sparse, like, of course, we don't want to take the click, then the question is not very interesting. So that there will be routing protocols with small r's. That alone is easy. But also you want what is called small congestion. So I'm not going to define it very formally, but that just means, let's say, that each vertex only participates in small number of these interactions. Like, it's not like everybody sends their message to one vertex and he passes it along. There is no huge bottlenecks. Yeah.
Is it deterministic? Like, I just choose a single path from SI to TI for, or is there some randomness in the way they choose the next?
You can do it deterministic, let's say. Yeah. Let's say that the protocol is a deterministic choice of paths. So here's a theorem of Alon et al., and this was improved by Nenadov. So the difference between these two works is whether the R is log squared or log, but it doesn't really matter. So they proved that as long as your graph G is an expander graph, sufficiently good expander, like the second eigenvalue is at most 0.01, you can indeed do it in logarithmically many rounds. And this is a great result, but it's not applicable to us, or the parameters that it gives us are not the best, because in our case, there are going to be corruptions. And it is true that you can still use this sort of routing things to get PCPs, and this was done by Polisuk-Spillman and by Dinur and Meir. But because of this, they lose some log factor, which is too expensive. And I'm not even going to tell you what this log factor is, but it's really unaffordable. It's not some little log that you want to save. It's really killing you completely. So now we want to study a more refined model, where you don't just want to route things along, but you also want to take into account that maybe there will be some corruptions along the way. Maybe some vertices refuse to cooperate. Maybe some edges completely break. Stuff like that. So this is what is called fault-tolerant routing. So now there are going to be faults, and we want to be tolerant against them. So classically, the model that was first studied by the crypto people is the model of vertex corruption, where after you set up your protocol, some adversary comes and say, I want to corrupt these vertices. And from now on, during the protocol, I'm going to control completely all of the messages that they send. They can fail to participate, or they can send garbage. They can do whatever they want. But nevertheless, as long as this number of vertices that are corrupted is small, I want most of the transfers to be successful. Okay, maybe let me go back to. So now I want to design a network where you can route things, but you are also tolerant against this type of adversaries that take control over a small fraction of vertices. Okay, so this was considered already in '86, and there have been a few works about it. And these papers get very nice results. So in particular, they managed to construct graphs with polylogarithmic degree and polylogarithmic work complexity, which is defined as the computational complexity that vertices do. But for this talk, you can just think about it as, let's say, the number of rounds. It's similar enough for us. And yeah, this is the result that I know. But this is not good enough for us, because it turns out that when you want to do PCPs, the correct notion of corruptions that you need to consider are what is called edge corruptions, as opposed to vertex corruptions. So what is the model of edge corruptions? Now, after the protocol is set up, the adversary is allowed to take control over a constant fraction of the edges, and then the adversary can choose whatever happens on them. They can fail to transmit, they can change the message, they can do whatever they want. And you can see that this is more power, because if I want to simulate a vertex corruption, I just take all of the adjacent edges and I completely control it. But this gives me more power, or gives the adversary more power. So it's more interesting to prove results against that. And again, the goal is the same: construct protocols which are tolerant against this type of corruptions. And somewhat surprisingly, this model was considered only by one of these works from the crypto people. And even that was some sort of black box reduction, saying that if you have some vertex corruption model result, then you can transfer it to the edge model. It gives you something, but the parameters are too weak for us. And what we show is an analogous result to vertex corruption model, but in the edge corruption model. And we show that in this case, there are polylogarithmic degree graphs that are fault tolerant against constant fraction of edge corruptions. And again, these are not simple graphs that I can just draw to you on the board. They come from HDX. Like you need to construct some big HDX and then take the underlying graph. So after all of that, I said the word HDX many times, and even though I assume that you all know what HDX are, let me still tell you a little bit of what are HDX and try to give you some sense about this result. No, so in fact, you can be quite generous. You don't need too special of HDX, like spectral expansion and maybe large enough, but constant dimension is enough. But you don't need co-boundary, you don't need a...
This is best possible?
No. So, no. So I saw it in the next slide. It turns out you can get it down to constant degree. Cool. So a crash course about HDX, okay, so I'm not really going to define anything. I'm just going to give you a feeling to what HDX is, which is sufficient for what I'm going to say. So here is my definition of expander. A graph is an expander if it looks like the complete graph. Or more precisely, if the adjacent matrix has small second eigenvalue. So in the same spirit, if I give you a simplicial complex, which is just, vertices, edges, triangles, like you've been through this business, you know what it is, which is downwards closed, then I say that X is a spectral expander if it looks like the complete complex. So I'm going to be more specific about that, but I'm not going to give you any formal definitions. Let me mention that when you talk about high-dimensional expanders, there are other notions of expansion that are even important for the context of this talk, but I'm not going to tell you anything about them besides their names, consistoric expansion and coboundary expansions. They're important when you talk about direct product testing, and maybe Izar will say a few words about them, maybe not. Okay, he said that no. Sorry. So they're very important, but we're not going to discuss them. So let's get a feel for what is actually spectral expander and not say like the complete complex. So the way I want to think about it is the faces of size D, I want to think about them as D-clicks. Indeed, they are D-clicks because of downwards closure. And the way I want to think about it is the following. So X is a good HDX if, first of all, it's sparse, like it doesn't have too many edges, but at the same time, it satisfies the following two properties which sort of contradict the sparseness. So it has large coalitions which are very well connected. These are the cliques. Cliques is a coalition which is very well connected, as good as it gets. And these cliques between themselves also have good interconnections. So it's not like there is one click here, one click there, and there is no connection between them at all. They have good interconnections in the following sense. So let's say that I have some click D1, and now I do some random walk, which from a click D1 goes to a click D2 that intersects the size D over 2. And I go on this walk for a while. So I want you to think about this good interconnectedness as this type of walks converge quickly. Cool. So this is my definition of spectral expanders. Okay? So now in the rest of the talk, I'm going to try to convince you that this is related to routing, and I hope that you will be convinced that it is related. So to do that, I'm going to change the game a little bit. I mean, it's a bit uglier if you don't change the game, but let's do it. So instead of the vertices themselves holding the messages in the routing game, I want you to think about clicks as holding a message, in the sense that for each click D, all of the vertices in it hold the message MD, the same message. And now the goal is to route messages between the clicks according to some permutation pattern. So if you remember the pairs SI, TI from earlier, now the pairs are going to be capital D and pi capital D. So
Totally can't see it this way.
Ah.
It works only if you project it.
only if I put. Okay, I'm not writing anything too deep here. I'm just saying that the pairs that I want to route between are pairs click D and pi D. That's all I was saying. That's my goal in life, and the way we're going to do it is by a protocol which we call the click-to-click routing protocol. And as the name suggests, in that protocol, at each round, a click is going to transfer its information to another click, and then to another click, until it reaches the desired click. And that's the protocol. It's very natural, but now we're going to spell it out in a bit more details. So the first step of the design of the protocol is to set up the paths between the clicks. So here you need to use spectral expansion. And using spectral expansion, you can show that you can find a collection of paths where each path is between a click C and the click pi C, let's say. And the length of these paths is logarithmic in n. So this is where I use the quick mixing. So I'm going to find this collection of paths, and there is some asterisks there, which says that this collection should satisfy more properties, like you don't want all of the paths to go via the same vertex or stuff like that. So think of them as like regular paths. So that's step one. Let's assume that we've fixed all of these paths. And now we're going to do the transmit of information. We have L rounds, where L is the length of these paths. And each round looks as follows. So at round T, I look at the click dt, and I want to pass the message to the click dt plus 1. So what I'm going to do is, well, the way we calculate the paths, 2 consecutive clicks have intersection of size d over 2. So I'm going to look at that intersection. And now, all of the vertices in click dt are going to send their message to the vertices in the intersection. So they send it, and then each one of the vertices in the intersection does the majority vote among all of the things that they received. So they compute the majority vote, they decide what is the value that they hold, and then each vertex in the intersection between dt and dt plus 1 forwards the message along to every vertex in dt plus 1. And then again, the vertices in dt plus 1 do the majority vote again. So let's say it again. In round T, I'm assuming that the click dt has a message. I want to forward that message to dt plus 1. What I'm going to do is I'm going to send all of the bits to the intersection vertices. I know that I have direct edges to there, because it's a click. Yeah, so I was just repeating what I said earlier. I was just describing the protocol again, that every vertex in dt sends the message to the intersection computes the majority, sends it to the next click, which again computes majority, and move to the next round. So let me tell you the idea of the analysis of this protocol. So I claim that if an adversary corrupts only a small fraction of the edges, let's say epsilon, then almost all of the transitions still go through. So for that, I'm just going to make one definition. I said that a click is bad if it contains too many bad edges. Too many is 2 epsilon. And then I have the following lemma, which says that if x in a HDX, then the number of bad clicks is small. And to get a, to get a hint for this, you can just compute the expected number of corrupted edges in a random click. You will see that that's epsilon. So we're asking here about deviations. And indeed, if you apply Chernoff bounds for expander graphs, which was proved by Yotam Dixon and Max Hoppins, it gives you that at most 2 to the minus square root of the dimension of the cliques are bad. So that shows you that, indeed, almost all of the cliques in the graph are not bad. OK, so we have this nice lemma. So now, for the path to go through correctly, it turns out that it's enough that each one of the cliques is not bad. And you can think about it, because like, if epsilon is, let's say, smaller than 1 over 100, you will see that all of the majorities are computed correctly, if the cliques are not bad. So the question is, what is the fraction of paths that contain no bad cliques? So number of cliques in a path is L. Probability that each one of the cliques is bad is 2 to the minus root d. So by union bound, at most L times 2 to the minus root d of the paths are bad. And if you choose the numbers correctly, let's say choose d to be log squared, you see that this is little of 1. So almost all of the paths go through correctly. So that's the click-to-click protocol. That's as bad as it gets. And if you sit down and formalize it a little bit more, it's an actual proof. I'm not hiding too many details here. And indeed, if you use this precise protocol, you can get a PCP. But it's not going to be quasi-linear, as I said. Rather, the size is going to be n times 2 to the poly log n. And this is because of the size of the HDX, which is 2 to the d squared times n. And in fact, the tolerance is even better than I said, but let's forget about that. And the way you use routing to get PCPs, so I'm not going to say too much about it, but you can use these sort of things to change the topology of a PCP. So initially, the queries the PCP makes are completely arbitrary. You don't know any pattern of the texture it makes. But it turns out that once you use routing protocols, you can design PCP verifiers whose questions are according to the edges of some graph that you like. So once you have that, you can actually get it to be something nice, and then you can do the randomized amplification. Yeah, cool. So if you want to improve it down to quasi-linear size, you do something similar, but it turns out that you cannot use cliques. That's too expensive. You need to use something different, which is a link, which is still very well connected, but it's not a clique. And you have a very natural link-to-link routing protocol, which is similar in spirit, but more complicated. And the idea is similar, but everything is messier, and you also need zigzag products and a lot of stuff. So, yeah, so that's all I'm going to say about routing protocols. So let me conclude. So in this talk, I told you about quasi-linear size PCP and connections to direct product testing and routing protocols. There are many open problems. So like the holy grail would be linear size PCP, even though it's not completely clear what it means, as I said. But there are more questions, like are there any other applications of HDX in PCPs? So after this work, together with Mitali and Kartik, we managed to use this stuff for some applications in fixed parameter complexity. And I think that there should be more applications of routing, but as far as what I described today, so we know how to get constant degree routing networks using the ideas here, plus some composition things. And finally, the way I think about HDX is there are sort of sparse objects that are nevertheless very well connected. And I think that once you have one application for something, there should be many. So that's it. Thank you.